let's explore this time slowing down a bit more. You're going to want your calculators out. We're going to do some quick calculator calculations. I wrote down here, Geo, why don't we notice special relativity in our everyday lives? Look at the time dilation equation. So let's write down the time dilation equation, which says t, time back home on Earth, equals t0 all over the square root of 1 minus v over c all squared. Write that down. You can copy it from your green sheet. We're on the back page. Alec, can you show Saki where we are on the green sheet? And then also later on, can you give her the velocity equation that we added last day? But do that later on, okay? Thanks, Alec. And what I'd like you all to do is take your pen or your pencil and circle that part. That square root e thing. We call this circled section the Lorentz factor. It's named after a mathematician scientist who first suggested its existence. So before Einstein published his paper, Lorentz had actually derived this function and said, I don't know why, but when I plug it in, now the numbers work out okay. But he couldn't explain why. So we don't give him credit for special relativity, but Einstein certainly knew of the mathematics that Lorentz had done. It's often symbolized with the Greek letter gamma. So sometimes you'll see this Greek, by the way, the Greek letter gamma looks like a fish doing a headstand, okay? You'll see it written as 1 minus v over c all squared. We call this the gamma function, the Lorentz factor. This is what determines, Ira, just how much time dilates. It's what's doing the dilating. So sometimes if you take this in upper level university, you'll see the time dilation equation simply written as that. Where that equals the square root of 1 minus v over c all squared. You can write that down if you want to, but we kind of have that in the box right above. So Jason, you don't have to write it down if you don't want to, but certainly you can write down the t equals t0 over gamma. Now that I show this, I have some kids that choose to write that as the formula because it's less writing, and then they just notice that the gamma is the square root of 1 minus v over c all squared. Okay. What I want to ask is, how much will 1 hour of time dilate for each of the following situations? And the way we're going to do that is we're going to get our calculators out, Alec, and we're going to calculate the Lorentz factor, the 1 minus v over c all squared, for each of these. First of all, for a human walking, and get your calculator out. So an average human walks at 2 meters per second. I'm going to let the v equal 2. You don't need to write that down if you don't want to. I'm just telling you this is what we're going to do. So Geo, where the v is in the Lorentz factor, I'm going to put a 2. C is going to be the speed of light, which is 3 times 10 to the 8th. Get your calculators out. If you go 2 divided by 3 scientific notation button 8, you'll get that. Double check when you hit equals if you get that. 6.6 repeating times 10 to the negative 9. Then I would square that. I would go 1 minus that answer, right? And you'll notice my calculator can't keep track of the decimals anymore, and I'm betting yours did as well. On this line here, I'm willing to bet, even though it should be 0.99999999999999999, and then a few other numbers, your calculator just gave up. Is that right? Y'all got a 1 instead of the decimals that should be there? So the Lorentz factor here is so close to 1 when you're walking. The difference between your 1 hour and somebody who is sitting still, their 1 hour, it's negligible. It's so small that my calculator can't track it. I did find an internet long number calculator that would actually track it, and I typed it in just for giggles, but okay. What about a race car? A race car Now V is going to be 70. Let's put a 70 in for the V. So I'm going to go 70 divided by 3 scientific notation button 8 equals squared equals 1 minus that answer. Brisa, even in a race car, the time dilation is so small, my calculator can't track it. For all intents and purposes, the Lorentz factor, the time dilation factor, is 1-to-1. People going in a race car don't age noticeably slower than people who are in the grandstands. You don't notice it. Okay, let's kick it up a notch. The fastest consistent man-made object that isn't a rocket ship is the SR-71 Blackbird spy plane. And that could peak out, rumor has it, because it's classified, at around 1,000 meters per second. It could go a kilometer a second. Okay, let's put 1,000 in for V. I'm going to go 1,000 divided by 3 scientific notation button 8, the speed of light. I get 3.33 scientific notation button -6 squared. 1 minus that. Duh. Even an hour on the SR-71, you still, although technically you have aged slightly slower, Elliot, doesn't show up. Okay. The Earth moves around the sun at 29,600 meters per second, which means time is moving slower for us than it is on the sun, because the sun is at rest relative to us. Maybe if people lived on the sun, would they notice that we are aging slower? So let's try plugging in, okay, it's going to be 29,600 divided by 3 times 10 to the 8th. I get 9.866, blah, 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 to the negative times 10 to the -5, squared. 1 minus that. Hey, ooh. And then, what's that all inside? A square root. Square root of that. Okay. Now that's on the bottom of the fraction. So if I want to figure out what 1 hour becomes, I'm going to go 1 divided by that. Because T0 on the Earth, which is our moving object, is 1. So I'm going to go 1 divided by that answer. 1 hour on the Earth is 1.1, 2, 3, 4, 5, 6, 7, 8 zeros and then a 5. Is that what you folks got as well? Yeah? Okay. 1, 2, 3, 4, 5, 6, 7, 8 zeros and then a 5 hours on the Earth. Calculatable, but still, I would argue, pretty negligible. The Earth and the Sun, our solar system, is moving throughout the galaxy at 2.1 times 10 to the 5th meters per second, which means time at the center of our galaxy is moving slower, Gracie, than time where we are. How much slower? Let's try plugging that in for V. 2.1 scientific notation button 5 divided by 3 scientific notation divided by the speed of light equals squared 1 minus that square root of that and then 1 divided by that to figure out the time dilation for 1 hour. So that 1 on the top is me plugging in T0 as 1. Is that okay, Matt? 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros, 2, 4, 5. Meh. Sarah, meh. Hardly makes a difference. Meh. UBC has a particle accelerator, a cyclotron. It's called TRIUMPH. It's an acronym. It stands for something, I can't remember what. But they get protons going at 2.28 times 10 to the 8. Let's plug that in for V. So it's going to be 2.28 scientific notation button 8 divided by 3 scientific notation button 8 equals 2.24. I said 2.28. I typed 2.24. I typed it right. 1 minus that equals square root of that. And then 1 divided by that answer. Do you get 1.986? Really, 1.99? Tasha, you got that too? Okay. So that means for those protons, now they are moving and we are sitting still. As far as the protons are concerned, if they travel for 1 hour, how much time has gone by for us? 2 hours. Because we're the ones sitting still now relative to the protons. Is that okay, Alec? Now we're making a difference. That's 2 to 1. At CERN, they get muons going 2.996 times 10 to the 8th. Now we're getting pretty close to the speed of light, which is 3 times 10 to the 8th. We should notice a bigger gamma function, a bigger time dilation. 2.996 scientific notation button 8 divided by 3 scientific notation button 8. 1 minus that square root 1 hour divided by that. So 1 hour for those protons, we get 27.4. Did I miss a step? I forgot to squared. Did I forget to squared with the previous one too? Now I'm terrified. I've got to double check. 2.24 scientific notation button 8 divided by 3 scientific notation button 8 squared equals 1 minus equals square root equals. See how my brain was bugging me? Ha! It's not 2 hours back here. It's 1.5 hours back here. Forgot to square, and this is wrong too. Ha! I'm making mistakes with Einstein. Good for me. This is tough stuff. I would never do this without showing work on a test the way I'm doing it right now anyways. Squared. 1 minus that. Square root of that. 1 divided by that. That makes more sense. 19.4 hours. Still a big difference. Last I checked, and this was about a year ago, we may have broken this. The fastest we were getting stuff going was at the Stanford Linear Accelerator, the SLAC, and we could get electrons going up to 2.9979 times 10 to the 8th. 2.9979 scientific notation button 8 divided by 3 scientific notation button 8. 99.93% of the speed of light. We can, at the Large Hadron Collider, get going faster than that, and we'll talk about that later on. Squared, don't forget the squared, 1 minus that answer, square root of that answer, 1 divided by that answer, and I get 26.7 hours would go by for us for every single hour that the electron experiences. Would you like to see time dilation illustrated in 10 seconds? You would. Put your pencils down. Now it gets really weird. Einstein, when he published his paper, Pierce, didn't just show that time dilates. Einstein's special theory of relativity makes other predictions about objects moving at speeds greater than 0. I'm not going to do the mathematical proof for this one, but Einstein proved that there was also something that happens to the length of a moving object. The length of a moving object will be measured to be shorter when it's moving than when it's at rest. This shortening is only seen, though, in the same direction as its motion. In other words, if you're moving forward or backward, the shortening will be in the forward or backward direction. If you're moving up and or down, the shortening will be in the up or down direction. We call this length contraction. Next page. Here is our next equation. If the length of an object when it's standing still is L0, the theory of relativity predicts that the object's length when it's moving at a speed v will be measured to be L equals L0 square root of 1 minus v squared over c squared. It looks very similar to the time equation, but instead of dividing by the square root, we're timesing by the square root. This is sometimes written as L equals L0 times the gamma function. And now you're seeing why I introduced the gamma function to you. Where L is the moving length and L0 is the original length at rest. There's a bit of a problem here, unfortunately. And the problem, Sasha, is in the time dilation equation, T0 is on board the spaceship, the moving object. Unfortunately, in the length contraction equation, L0 is the original length at rest, not moving. And I haven't figured out a good way to help you keep straight those two issues, except to say in the L, I think L original, and in the T, I think time on board. They both begin with O, though, so it doesn't help much. This part you'll have to memorize. So, let's suppose a meter stick went shooting past you at 0.995 C. How long would it look to you? This wants us to find the moving length. That must mean they gave us the original length at rest. This is so obvious that it's tricky. What's the length of a meter stick at rest? 1. How fast is the meter stick traveling? 0.995 c, 99.5% of the speed of light. If it zipped by you that fast, and you could see it that fast, which is tricky, but maybe we have an instrument that lets us do that, how fast would it look to us? Well, L equals L0 square root. By the way, this is also on your green sheet, yeah? The length equation? 1 minus V over C all squared, or V squared over C squared. It's the same equation. The original length is 1. Square root of 1 minus 0.995 C over C all squared. Henry, do you see? Yeah. Do you see? 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 So now I can go to my calculator. I guess inside the square root, I'm going to have 1 minus 0.995 squared equals square root of that equals 1 times that. And you would see the meter stick as 0.0998 meters, about 10 centimeters. You would see the meter stick about that long. Yes? 2 9s and an 8. Oh, sorry, 2 9s and a 9. Thank you. I can't believe I did that, Tato. Candy for you. Remind me later. That's about 10 centimeters, though. You would see the meter stick about that long. Even though on board the spaceship, they would see the meter stick as a meter stick. Wow, yeah. Suppose we build a spaceship that's 85 meters long, and it passes you at 2.23 times 10 to the 8th meters per second. How long do you perceive the spaceship at since you're at rest? Let's see. What's this question wanting us to find, L or L0? L, the moving length. That must mean they told us L0. And they told us the speed, 2.23 times 10 to the 8th. This one they gave us in meters per second, so unfortunately this time I'll have to plug in C as 3 times 10 to the 8th because there isn't a C tucked into my original V. Do you see? Do you see? Sadly not this time. I'm going to get, again, L equals L0 square root of 1 minus V over C all squared. 85 square root of 1 minus, and I guess it's going to be 2.23 times 10 to the 8th over 3 times 10 to the 8th, whatever that is, squared. 1 minus that. 2.23 times 10 to the 8th divided by 3 times 10 to the 8th. Whatever that is, squared. 1 minus that. Square root of that times 85. And I get the ship as 56.9 meters long. Now that's in the direction of travel. Really, it would look like when you resize a document in one direction, but you don't resize the photo in the vertical, everything would be smooshed together but seem really tall. Example 3. Suppose a spaceship is 100 meters long when stationary. When it moves past the observer measures the spaceship to be 25 meters long. How fast is the spaceship moving relative to the observer? What's this question want me to find? That must mean they gave me L original. How long is this when it's at rest originally? 100? Good. And that must mean they gave me the relativistic length when we're moving? 25. I need to get the V by itself. I'm just going to give you the punchline, and we're going to add this one to our green sheet as well. It turns out I did this on pencil and paper. If you get the V by itself, you're going to get V equals C times the square root of 1 minus L over L0 all squared. It's really similar to, add this to your green sheet, please. I would add this maybe right underneath or right near the L equation. It's really similar to our other V equation, but I think our other V equation, inside the square root, the T0 was on top and the T was on the bottom. And so you can see there is potential, Pierce, to make sloppy mistakes here. It's Einstein. Be careful. So in the speed equation for length contraction, the L is on top and the L0 is on the bottom. You've all added that to your green sheet? Are you allowed to have that on your test, Matt? Absolutely. Okay? Let's give this as an answer as a percentage of light first. So let's leave the c there. And let's go 1 minus 25 over 100 squared. Really, what if you want things to appear 4 times shorter? 25 and 100, that's a 4-to-1 ratio. Okay. 25 divided by 100, that should give you 0.25, I hope. Squared. 1 minus that. Square root of that. And I get 0.9682, 0.9682c. What is that as a percentage of light? 96.82% of the speed of light. You know what? I have a symbol for the speed of light, don't I? What letter is our symbol for the speed of light? I'm going to use that. I tend to abbreviate. Or if you wanted it in meters per second, I could actually multiply this by the speed of light. I could find out what is 96.82% of means multiply. In meters per second, 2.905 times 10 to the, oh yeah, because it's really close to the speed of light, it's going to be 10 to the 8th meters per second. 2 more, we're going to hit pause. A certain star is 15.6 light years away. How long would it take a spaceship traveling at 95% of the speed of light, 0.95c, to reach the star? First of all, relative to us, and we're stationary, underline the word stationary, relative to us on the Earth. Since on the Earth we're stationary, are we traveling at relativistic speeds? So you know, we don't need to use relativity. We can actually say d equals vt plus a half at squared, but we're ignoring acceleration because we don't know how to deal with that yet for relativistic stuff. A asks, how long? What do they want me to get by itself? T. It's going to be the distance divided by the speed. The distance is 15.6 light years. The speed is 0.95 light. The light and the light cancel out. Really, I'm going to go 15.6 divided by 0.95, and that's going to give me an answer in years. As far as we're concerned, it's going to take 16.42 years to get there. Sarah, will that be what the spaceship experiences? No, because time is going to be different for them, right? As measured by the observers on the spaceship, I think now they want us to find time on board. What's T? 16.42 back on Earth. Good. V is 0.95 c. So now we're going to use the time dilation equation. Alec, we want to get the T0 by itself. Look at your green sheet on the time dilation equation. How would I get the T0 by itself? What will I do with that big square root thingy? First of all, I want to just move it to the other side. What is the square root thingy doing to the time 0? See it? Right? The type. Yeah, so how will I move it over? Yes. I'll get time 0 equals time times the square. Oh, hey, if you really want it to be nerdy, you could do that if you want to do less writing, but I'll write it out. This is why, by the way, because you're writing that stupid thing so often, they have a symbol for it, right? Square root of 1 minus v over c all squared. It's going to be 16.42 square root of 1 minus 0.95 c over c all squared. Alec, do you see? Do you see? Do you see? Hey, the c cancels this time. It would be even funner if this was in a Spanish class, because then I could say, do you see? And you would say, see. You see? Yeah, okay. It's going to be 1 minus 0.95 squared, square root of that, times 16.42. Oh, careful, Mr. Dewick. On the spaceship, $5.13? Is that right? Oh. C asks, what's the distance traveled according to the observers on the spaceship? I want you to draw a little line down the middle of your page right there. One way to find the distance would be to go like this. Distance equals v times t0, the time that the spaceship experiences. And so we could go, what's v? 0.95 c. And what's t0? 5.13 years. And can you see I get light years in my units? This is going to give me a light year if I just multiply those numbers together. And this is what we did last lesson when we looked at, I think we went to Proxima Centauri or something like that. We did it this way, 0.95 times 5.13, and I get 4.87 light years. So Einstein had run that numbers, and he said something weird's going on with length. The other way to do this is actually to use our new length contraction equation. L0 is the original distance, which was 15.6 light years. We would like to find L, the moving distance that the spaceship experiences. Okay, L is going to be L0 square root of 1 minus V over C all squared. $15.6 is what we think it is, because we're at rest. That's what we measure the distance. Square root of 1 minus 0.95 C over C all squared. This is kind of nice. Do you see? Do you see? Do you see? I get 1 minus 0.95 squared, square root of that, times 15.6, and I get the same answer, 4.87. This is the mathematical proof that this length contraction works, because we got the same answer using the time contraction equation, which I did prove, with the time dilation equation, which I did prove. So we get 4.87, and since we put in a length of light years, we would get an answer back in light years. Ready to kick up the weirdness? So what does this mean for an object that travels at the speed of light, like a photon? What happens if you take this equation and you travel at light speed? You put a C in for the V. Well, if you put a C in, if you travel as a photon, what's C divided by C? Squared? What's 1 take away 1? What's the square root of 0? For a photon, what are all distances equal to? So I already said to you that a photon, when it leaves a star millions of light years away, it gets here instantly. It's even weirder than that. It doesn't travel the distance in between because a photon is everywhere in the universe at once because it doesn't experience distance at all. When you turn on a flashlight and you see light coming out of the flashlight, photons coming out of the flashlight, as far as those photons are concerned, they're everywhere throughout the entire universe at the same time. Oh, come on, that's pretty cool. I have a take-home quiz for you. And somebody else has asked about time travel, so here's another way you could time travel.